Well, firstly, I like to apologize because I got a heavy cold, so my voice is not quite strong. In fact, I can hardly speak, but no problem, as long as you can understand me. So we are here. We have here an exercise with three sections, but we are going to do one by one. The first section says the following: implement a full adder using as few MUX1 as possible. Okay, so we have to use the MUX1 combinational circuit to implement the truth table of a full adder. We don't know to we don't have to know the full adder truth table by heart. We can just build the truth table as in any other case. So we are going to remember what a full adder is. If you remember from the last part of topic 5, when we saw the arithmetic blocks, we saw that the simplest version was the half adder, but the half adder didn't consider a possible previous carry of a possible previous sum of 2 bits. So the full adder takes into account a possible previous carry. So a full adder was something like this, in which we have the sum bit and the next carry bit, and the input were one bit, another, and a possible previous carry. So we have to implement the truth table of this. That is quite easy. So our inputs are x and y and the possible previous carry, and the outputs are the next carry and the sum bit. So we have three input that correspond to 8 possible combinations. We write all of them, and we just sum the bits. 0 plus 0 plus 0 is 0, and the next carry is 0. 0 plus 0 plus 1 is 1, with a next carry of 0. 0 plus 1 plus 0 is 1, with a next carry of 0. 0 plus 1 plus 1 is 2, so we have 0 at the sum bit and 1 in the next carry bit. 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 2. 1 plus 1 is 2. And 1 plus 1 plus 1 is 3. Sorry, I changed just in the last row the kind of pencil of the tablet. Okay, so it's like this. So we already have the truth table, so we are going to obtain the functions. We are going to build the Karnaugh maps. You can note that this is always the same. To obtain the functions, we use a Karnaugh map. For the next carry, for example, and for the sum bit, the other output. And now from the truth table, we fill both Karnaugh maps. So here we have these ones, and in the sum bit we have these ones. And now we simplify. In the case of the carry, we have this implicant, this implicant, and this implicant. All of them are essential prime implicants, so they are going to be in the function. And they are xy plus x by the carry plus y by the carry. The sum bit, well, here we cannot form any larger prime implicant because the ones are isolated. So we have to take all of them into account. And we are going to have xy negated c, xy c negated, xy c, xy negated c negated. So we have our functions, and now we have to implement them with mux once. Remember that in a mux1 we only have one selection input. So well, it's not the best option, but it's what we have. The fact is that we cannot simplify this thing a lot because we have some columns with all zeros, for example here, but we cannot use as selection input xy to cover this column. But we are going to know that in the case of x equals to 0, we are going to have here a 0. The thing is that you can check all the combination as you want, but you are not going to be able to simplify a lot the functions because of the kind of multiplexer we are using. We are going to start, for example, with the carry functions. So this is a mux1. Here we can use, for example, as selection input the carry because it's going to be easy to look at the rows. So in the case of the previous carry is 0, sorry, I forgot to put here this. Is 0, we have this this row. This row is not a constant. It's not either the value of one of the variables of the columns. So we cannot implement, as I said, really a simplification. So we need another mux, and we can use, for example, dx. So when we are here in the previous carry equal to 0, we are in this row. When x is 0, we are here because, well, I don't want to confuse that with implicants. When x is 0, we are in these two cases. So the function for this combination, you can see that is always 0. So we connect here a 0. Well, that's a little simplification, but finally we are using the same number of mux1 using the selection input that we want. You can check it. You can try to change and, for example, choose here x or y or in the others, and you are going to get always 3 mux2. Sorry, 3 mux1 because we cannot simplify more. So when x is 1, we are here. And we can see that the value of the cell is the same here and here of that of the variable y. So here we can connect y. And when the previous carry is 1, we are here. We are here in this row now. We are going to see what happened with x. with x, when x is 0, we are here, and the cells have the value of the variable y, 0 and 1, so we can connect y. In the other case, when x is 1, we are here, and both cells are 1, so the function there is 1. So we have the next carry implemented with MUX1. Remember that the one is that they have one selection input. So now we have to proceed with the sum bit, that is this one. I'm going to try to move it because it's not quite visible here with this little menu. Okay, so we have to use again MUX1. In the case of the bit sum, we can see that the distribution of the ones is kind of a mess. We have our prime implicate are all essential prime implicants, and they are min terms. They have all the variables in the product term. We don't have a row that with a constant value. We don't have any variables of the Karnaugh map that is with the same value of the cells. So we cannot do a really good scene simplification. We are going to follow the same approach as before. For example, we are going to select, sorry, I'm going to change this, to select in the last stage again the previous carry. In the case of 0, we have another MUX1, and we are going to follow the same approach. For example, connecting x. You can connect here x, y, or change the order. You are going to obtain the same number of MUX. So now we are going to do as before. In the case of c equal to 0, we are in this row, and when x is 0, we are here. X is 0, we are here. There, the cells have the same value of y, 0, 1, 0, 1. So we can connect here y. And when x is 1, we are here. And in this case, the cells have the opposite value of y. So here we have y negated. When the previous carry is 1, we are here. When x is 0, we are in the first two cells, and the cells have the same values of, the opposite values of y. So here we have y negated. And in the case of 1, we are here, and the cells have the same values of y. So we can connect here y. We haven't finished because we need y negated. So we are going to use an extra multiplexer to negate the y. Always that you don't have in an explicit way in the exercise that you have available the negated versions, you have to implement the negated version. So you cannot have them for granted. You have to implement them. So here we are going to implement y negated. That is really easy. When y is 0, the input is going to be 1. And when y is 1, the input is going to be 0. It's quite easy. So here we have the sum bit implemented with MUX2. You can check if there are combinations in which none of the variables are negated, so you can save this MUX. But I'm going to tell you that there is no that combination. Choose the variable you choose for the selection input. You are going to have one of the variables negated because the min terms are in positions of the Karnaugh map in which negated variables appear. So this is two versions that are the minimal, in fact. You can check the combination you want. You are going to have the same number of multipliers 1 for C1 plus 1, Cy plus 1, sorry, and xy. So this is the first section, and we have done. We are going to do the second section of the exercise. Let me clear this and have some space. So in the next section of the exercise, we have to implement the necessary output using a decoder with negated outputs. We can choose the decoder that we consider necessary, and we can use as well a logic gate. So which decoder are we going to use? We have 3 inputs, so we need a decoder from 3 to 8. Remember that the output is going to be 2 raised to the number of inputs. So this is the decoder. We have 3 inputs, the input of our full header, and 8 possible outputs. And the outputs are negated. If you remember from class, it means that we have here small circles. That means that we have here the negated version of the outputs. So here we are going to have the negated min terms, the min terms formed by our inputs. Remember, min term 0, min term 1, etc. The 8 min terms that we can form using these 3 inputs. So we saw this in class. So just we need just another gate to group the the output that we are interested in. We can use the min terms or the max term. For example, if we use an AND gate, we have to use the zeros of the function, the max terms. So the max terms here are these combinations. Sorry, this, and this. So max term 0, 1, 2, and 4. Zero, 1, 2, and 4. And we have to demonstrate that this is correct. And we have here, sorry, that we have here the function they ask. So we are going to build the function. We are going to be the AND operation, that is a logic product of min term 0 negated. Remember that the circle, as I said, is the negation, multiplied with the logic product by the min term 1, the 2, and the 4. And what is a min term negated? Is the max term not negated, associated to that combination of the inputs. So we have here in fact the max term 0 multiplied by the max term 1, the max term 2, and the max term 4. And here we have a product of sums, a product of max terms. This is the conjunctive canonical form of the function. So we have implemented the next carry output using this combination. But we have another option. I'm going to show you the other option. You can choose the one you prefer. We can use the minterms negated, but instead of using an AND, we can use an AND gate. And in this case, we have to select the minterms, so the output for which the function is 1. I'm going to show you this. So now we are going to select the minterms of the function, not the max term. So we select 3, 5, 6, and 7. And what do we have at the output? Let's see it. This is with the NaN, and this is with the AND. With the NaN, we have the logic product negated of the selected minterms that are the 3, the 5, the 7, and the 8. So the output is negated according to the exercise specification. And here we have an AND. So if we apply the De Morgan's law here to break this negation, the big negation, we are going to have this. Just changing the logic product by a logic sum and breaking the negation. And we know that the double negation is equivalent to don't have negation. And this is a sum of minterms. And in fact, as you know, this is the disjunctive canonical form of the function. So we have the function using a decoder with negated outputs, either using the max term or the minterms, and obtaining the function in conjunctive canonical form or disjunctive canonical form. So we have finished these second sections. We have still the last section, the third section. Let me clear the screen and we'll do it. So finally we have to implement the output with the sum bits with as few mux2 as possible. Remember that the mux2 have two selection variables. Well, if we look at the Karnaugh map of this function, well, it is 1, and we saw that it's kind of a mess. So we cannot group variables to have constants in rows or columns. None of the combination follow the value of the cell follow the same value of any of the variables. So we cannot do simplifications using the methods that we know. So we are going to select, for example, in the output mux, in which we have two selection variables, just for the sake of simplicity, we are going to use xy. This way we can check the Karnaugh map column by column, following the combination, and it's going to be convenient and comfortable to use. So for the first combination, we are in this column. xy are 0, 0. And we can see that the value of the cells is exactly the same of the values of the previous carry. So here we can connect the previous carry. For 0, 1 we are here, and we can see that we have negated the previous carry negated. And I put it right here above the line because we have to connect, as you know, another multiplexer to have the negated version. So for 1, 0 we are here, and we have again C negated, and for 1, 1 we have here in this final row, and we have the same value in the cells of the value that we have in the previous carry. So we can connect the previous carry here. And now we have to implement the previous carry negated. and we can use one mux for the two of those inputs. So I just need a mux1 to negate a variable, but we have to use mux2. We are obliged to use mux2. So, as we have done before, we are going to cancel the combination we are not interested in. So if we connect here a 0, this is going to be a constant, so we are going to be always in these two combinations. These two that start with 1 are not going to be possible ever. So here we connect the previous carry. When the previous carry is 0, the input is going to be 1. And with the previous carry, when the previous carry is 1, the input is going to be 0. So this way we have here the previous carry negated. And the other input that we are not going to use, we can connect them, for example, to 0 or to 1. It doesn't matter, because they are not going to be used never. Normally we connect them to 0 because we connect them to ground. You know that ground is a 0 volts, but you can connect them to 0 if you want. I don't mind. So we have here the sum bit implemented with mux2. You can check another combination, but as I tell you in the first section, you are going to have the other variables negated. So finally you are going to use always at least 2 mux2. So this is the whole exercise. This is a real exercise from an exam. I don't know which year, but this is an exam exercise. So don't be afraid when you read the specifications of the exercise, because if you read it, keeping your mind cold and carefully, it's just build a truth table, build functions, and apply this specification of the combinational circuit. And it's not as difficult as it may seem in the beginning. So okay, we have finished.